Now, firstly, about why relaxation actually happens. Why would spins spontaneously return to thermal equilibrium? The reason for that is noise, which is inevitable in any physical system. And if you take, for example, the magnetic field of your magnet, so Bz, the vertical amplitude of the applied magnetic field, and plot it as a function of time, what you would see if you position, a hypothetical tiny magnetometer at each nucleus is not just the magnet field. So let's say this is 14.1 Tesla, and we expect the magnet to be reasonably electrically stable, and so this is our magnetic field. What we would see, however, is not just that, we will see that plus tiny noisy fluctuations around them. So something like that. Utterly unpredictable at the point of the nucleus. So at the nucleus. Now the amplitude of these variations is tiny. It's really tiny. So we would be talking, the amplitude of that would be of the order, in terms of the effective Zeeman frequency, we're talking 10 kilohertz or so. And the time scale of these things would be in the picosecond to nanoseconds. So this, picosecond to nanosecond time scale. Now the principal reason for why this noise is present is the molecular environment. Imagine you have your little nucleus, and of course it's sitting in solution. There are other molecules nearby, which means that there are other charges nearby. Molecules have polarized bonds, therefore charges. And a moving charge is a current. As soon as you have a current, it creates a local magnetic field. And so everything that moves around your molecule is a collection of random currents, which would then create a collection of random magnetic fields. If your molecule itself rotates, what would happen is there will be current loops, the so-called spin rotation interaction. It will have its own interactions which are directionally dependent. This would put noise into the Hamiltonian itself. That is to say, there are multiple physically distinct and unavoidable sources of noise in physical systems that manifest itself in the noise in the magnetic field, longitudinal as well as transverse. What would then happen is that this noise would have a number of frequencies if we plot the power density of the noise as a function of the frequency of the noise. Well, if you look at it, right, this noise will have some collection of frequencies. It will have one amplitude at one frequency and a different one at another. Generally, these are decaying lines, so we would say that these ranges in here are of the order of about 10 to the 9th radians per second. That's the relevant noise scale in here, and so at each of the frequencies the noise would have some what is called a spectral power density. And this just happens to be our transition frequency. So we have our energy level, one corresponding to spin alpha and another corresponding to spin beta, and then we have this, that's our omega naught, that is minus gamma b naught, which is also in radians per second is of the order of 10 to the 9th, right? We are talking hundreds of megahertz in here. And so this noise, with its spectral power density, will just be hitting our transition. So in the same way as it happens in optical spectroscopy, vibrational spectroscopy, if we are shining some electromagnetic fields at the system at the right kind of frequency, we will be inducing transitions. But in those cases, these frequencies are usually controllable because you decide what the wavelength is of either the radio frequency or the infrared or the optical beam. But here the frequencies come from the noise. And so occasionally it will have some frequency here that hits our transition frequency, which will just randomly flip the spins around. Now, because we are dealing with a thermodynamically non-equilibrium situation, originally the rates of spin flip will be different in the up direction and down direction because we have different populations of the two levels relative to thermodynamic equilibrium. The result will be that the system is driven to the thermodynamic equilibrium at whatever temperature that our noise, figuratively speaking, has. So we have some oscillations that will be inducing random transitions. A great number of random transitions over a very long time are going to equilibrate our system. A very basic example of this happening is in your handout. What I've done is I've just numerically run a simulation on a bunch of noisy oscillators. That is, it is an oscillating just a ball on a spring where the force constant of the spring has a little bit of noise in it. And then if you plot that coordinate of that oscillator, so for example the x coordinate of our ball on that spring as a function of time, then each individual oscillator will just have a little bit of noise. It will be a sinusoid, but not quite. It will sort of be an erratic kind of sinusoid because of that noise in the spring constant. And then you record another system, and of course it will also be a sinusoid, but it will be erratic in a slightly different way, and it might slowly go out of phase with the previous one. And then the next sinusoid comes, and again it will have its own different instance of the noise, and it will get out of phase in a different way. Well, it stands to reason here, you see, that if we now sum this up, which corresponds to an ensemble average in a physical system, that the sum of this initially will be coherent, so you will have an oscillation because they all match, but will eventually go out of phase because in here and probably there, these sinusoids, because they go out of phase, they're going to cancel each other. And the result of this, if we plot the average in thick black line in here, is that there will be a signal that is going to decay. And this, in our parlance, in magnetic resonance, is transverse relaxation. And spins irreversibly go out of phase and the signal vanishes. Likewise, if we have noises in Bx and By, what will be influenced, if you remember the mathematics of Bloch equation, is the longitudinal magnetization, and then the longitudinal magnetization will jump up and down randomly in each individual spin, but the ensemble average will be driven to the thermal magnetization, and this classically at the hand waving level, why spin relaxation happens. Now, it stands to reason as well here that we are talking about probabilities of the individual events and a certain probability per unit time, and it's the same kind of mathematics as the mathematics of radioactive decay. You have your atom of plutonium or whatever it is, and it simply has a probability per unit time of decay. It may persist indefinitely if we are singularly lucky, but sooner or later it will decay. You know that macroscopically this leads to first order kinetics. And so what people did is they measured these relaxation rates for longitudinal magnetization, for transverse magnetization, and they discovered experimentally initially that the spins appear to relax at two different rates. One rate for the transverse magnetization and another one for the longitudinal, which stands to reason because there are physically distinct different magnetic fields being applied along the two axes. So, what they came up with is they said, okay, in the absence of precession, let's say they're sitting precisely in the rotating frame of each nucleus, dmx by dt is minus 1 over T2mx, where T2 is just, it's a historical name, it was called T2, the characteristic time with which this magnetization approaches zero. The same for my. dmy by dt is minus 1 over t2 my. And you know from your standard chemical kinetics that under such equations both mx and my will decay to zero, which is what we practically see, like transverse magnetization eventually disappears. However, longitudinal magnetization doesn't disappear, it goes not to zero but to the thermodynamic equilibrium value. So we would like such an equation of motion just empirically, we're like hacking it together. An equation that would drive, instead of the magnetization, it would drive the difference between the magnetization and the thermal equilibrium to zero. So let's say we want something like this. The difference between mz and equilibrium by dt must be different time called t1 than mz minus equilibrium. Now the mz depends on time, but m equilibrium does not. So in this equation, this is a function of time, but this is just a constant. So when we take the derivative, this will disappear, and this gives us the last equation. dmz by dt is minus 1 over t1 mz minus m equilibrium. So this equation drives the difference between the longitudinal magnetization and the thermal equilibrium magnetization to zero with the rate constant 1 over t1. And that's our system. Now you are all third and fourth year chemists. You have suffered extensively through the chemical kinetics. So you all can now tell me what solutions are to this. I probably wouldn't even ask. Now mx and my are generally interchanging so rapidly that we can just call them m perpendicular, and what we have therefore is mx of t is the original value of the perpendicular magnetization, so m perpendicular e, let's call it x minus t over t2. It will simply decay to zero. Standard first order kinetics. Then my of t will likewise be m perpendicular exponential minus t over t2. This equation's interesting, however, and unless you have attended my advanced mathematics option module, you would not actually know how to solve it. So this is quite instructive, and two experimental methods for measuring T1 come from this, and so I will actually spend some time and I will solve a non-uniform ordinary differential equation for you. So here we have dmz by dt is minus 1 over T1 mz plus m equilibrium over T1. Now this is chemical kinetics with a source. If this were a chemical reaction, that would mean that our mz is reacting away with this rate constant, but somebody is sitting there and continuously adding new magnetization to the system at some constant rate. This is in fact the source, it's the thermal equilibrium that is there. Okay, now this is what's called a non-uniform OD. You know how to solve this. Now the way we solve the complete one is by variation of coefficients. There's a very deep theorem in mathematics that says that whenever the dynamical generators add, the corresponding solutions multiply. So we will be looking for mz in the following form. We will say that our mz of t is the solution to the uniform equation, this one. So it will be exponential minus 1 over t1 t, but multiplied by an unknown constant, c of t. And if we now substitute this into the original equation, then this variation of constant method, there is a theorem in mathematics about this, guarantees us that we will obtain the solution to the non-uniform one, but we will check that in due course. Okay, so let us take this candidate solution with an unknown function and plug it into our full non-uniform equation. So you can see that essentially what we did is we accounted for the dynamics that we know how to solve, and that's the exponential, and we assumed that the correction in the case of the extra source is multiplicative. And there is a rigorous proof for that in the deep dark mathematics that I don't have the time to cover. Okay, substituting that in. So we will have d by dt of c of t e minus t over t1 equals minus 1 over t1 c of t e minus t over t1, and then plus equilibrium over t1. Product rule for that thing. So we will have here d by dt c of t times the exponential minus t over t1. That's this prime times that. So plus c of t and then that prime. So it's a minus here 1 over t1 e minus t over t1, and that's equal to the original thing, minus 1 over t1 c of t, and then e minus t over t1 plus equilibrium over t1. Notice that the biggest terms present all cancel, so we have that and this actually destroying each other. This always happens in these substitutions. This is why they are designed this way. And then let us move the exponential over to that side, and we get a neat little uniform equation for our CT. d by dt c of t is equilibrium t1 e plus t over t1. Lovely, and this can be integrated directly now. We say we separate variables. D c of t is equilibrium over t1 e plus t over t1 dt. So I put all c's on one side and all t's on the other. Integral here, integral here. So what's going to happen is another instance of that will pop out and cancel the t1. So we have here c of t plus a constant, let's call it a, equal to m equilibrium over t1. The integral of that just gets us t1 e plus t over t1 plus another constant b. A sum of two constants is another constant, and so our c of t is m equilibrium e plus t over t1 plus a constant, let's call it again a. And the last thing we need is to substitute that into our original candidate solution and simplify things. So we plug this c into there. So our final mz of t will be that thing. So m equilibrium e plus t over t1 plus some constant a times the exponential minus t over t1. And you can see if we open brackets, things will cancel. This exponential would disappear here, and it would reappear on the constant. And so finally, our solution to the differential equation here can be written in the following form. mz of t is m equilibrium that cancels that, plus some constant E minus t over t1, where this constant will depend on the initial condition. It depends on where we start from. Now notice here that we have achieved what we had set out to achieve. When time goes to infinity, when t becomes large, this exponential becomes very small, it drives this entire term to zero, and so we are left with the thermal equilibrium magnetization. However, at some other time, it goes to that thermal equilibrium magnetization from wherever it had originally been at the rate t1. And if we now take this and we substitute it into the original differential equation, we will realize that that is in fact a solution. And I will keep this A here for now because it is the difference between the two methods of measuring T1 and T2. Now, you will notice that although the solutions are fairly rigorous for this, that we more or less guessed the differential equations that we were solving. We said, well, okay, we're measuring some kind of decay and it looks more or less exponential. Let's just put together a bunch of exponentials that are going to have some decay. This is empirical, and as far as magnetic resonance imaging goes, actually pretty good. It's not very often that you see strong deviations from this kind of behavior, unless you are specifically searching for it. Notice another thing, that we have assumed that our magnetization is all exactly in the rotating frame. Of course, the next thing we must do is go back into the laboratory frame to see how all of this is going to behave if we do not make any assumptions about the frames that we are in. Well, it's just a coordinate transformation, and so really the only thing that's going to happen is the equations will acquire, the differential equations will acquire their oscillatory generators, and the solutions will just have a cosine and a sine. So I will remind you what Bloch equations had been for these things, and I will then modify these Bloch equations to also include the decay. We had d mx by dt. It was, if memory serves, the minus was here, omega my, and then my by dt was plus omega mx, and dz by dt was 0. Because it didn't precess in that particular direction. Let me just see if I've got my minuses the right way around. Yep, I did. And the solutions have been a sine and a cosine. Now what we simply do is we merge this decaying dynamics with the oscillatory dynamics by just adding up the right-hand sides. Again, there is a very deep mathematical theorem as to why this is done this way, but we don't have the time to look at it. 1 over t2 y, and here instead of 0 we simply have the decay. 1 over t1 mz minus m equilibrium. So these are the Bloch equations in the presence of relaxation. By the same argument as what I just demonstrated to you for the mz, the dynamics is a product of the dynamics that is oscillatory and the dynamics that is decaying. So in the special case where we begin at mx equals 1 and my equals 0, what we will have in here is cosine omega t, here we have a sine omega t, and here nothing is going to change. And so actually, after the dust has settled in these equations, we are getting exactly the picture that I have drawn for you at the very beginning. We have a decaying oscillation. Now, the microscopic reasons for why these individual trajectories will go out of phase and then sum up into a decaying exponential, those reasons would be really complicated, usually, and there are whole separate lecture courses at the PhD level about what and how drives spin relaxation and what information you can extract out of it. But empirically, at the very end, these are the equations that it obeys. Now, imagine that you've got this relaxation. It will have dependence on the statistics of the noise that the system sees. That noise will be relating to how rapidly the molecules rotate in solution or how rapidly things are moving around them, which then clearly tells us viscosity. And so there will be fluids in the body that are rather non-viscous, almost as viscous as water. So what comes to mind is cerebrospinal fluid in the cavities of the brain, various sort of non-viscous things like blood, relative to highly viscous things like fatty tissue or muscle tissue, so the cellular matrix and such things. And so you would expect that the relaxation properties, therefore, of cerebrospinal fluid would be very different to the relaxation properties of the surrounding brain. And so T2 relaxation, for that reason, is one of the principal sources of contrast. Not only that, it would also give us local information. For example, the viscosity of the inside of the erythrocyte is different from the viscosity of the blood plasma around it. And so by measuring that viscosity, even if magnetically like that, we can tell where some glucose molecule actually is if we measure the signal of that molecule with NMR. Right? The corresponding magnetization will decay at different rates depending on where the molecule is. In protein NMR spectroscopy, actually, because these things are driven by the dynamics of nearby particles, these rates start depending on interatomic distances. We will get to that spectroscopy in a few lectures' time. And by measuring relaxation and cross-relaxation and magnetization exchanges between the nuclei, you can measure intramolecular distances. And of course, for a protein, if you've measured a distance between every atom, you more or less know the structure. And this is how much of structural biology operates these days. So it's actually singularly important to be able to measure these things, and we will now again hook together a bunch of sequences that allow us to measure these things. We will start with measuring the longitudinal relaxation. Let's do something like the following. We will take a system. We will do a 180 degrees pulse, doesn't matter X or Y, it will flip the magnetization completely down. We will then wait for a certain period tau, so the magnetization got flipped down. After a period tau, it starts relaxing. It's not rotating back, it's like crawling on the Z-axis, back to the thermodynamic equilibrium. And after a prescribed period tau, we will give it a pi/2 pulse, at which point it will end up in the transverse plane, therefore becoming detectable, and then we will detect the magnetization, and then we will Fourier transform and integrate it. If we now plot this magnetization as a function of tau, so this is the magnetization that's being detected, and that is the time. Perhaps I should draw the axis in the middle here, like that. Here we come to this wonderful solution that we have. Let us actually find the A. At the level of the differential equation, this was an indeterminate constant. Any A satisfies the original equation. But now we know that at time 0, our mz was actually exactly minus m equilibrium, because we've inverted it. So we have additional information that says mz of 0 is minus m equilibrium. Well, and that means that if I put 0 here now, what is going to happen is we will have m equilibrium plus a, because the exponential becomes 1, must be equal to minus m equilibrium, Therefore, A is minus 2 m equilibrium. Therefore, mz will be m equilibrium 1 minus 2e minus t over t1. We found A for this particular case. Let's think about what this does. At time equals 0, the exponential is 1. This is minus 1. We have minus m equilibrium. So we are at the point where we have inverted the magnetization. So this is mz, but it is being detected after we put it in the transverse plane and integrate it in. Exponential starts fading away. This minus thing becomes smaller, so magnetization starts to recover in the positive direction. And then at some point it crosses 0, and when time becomes infinite, this entire term disappears and we go back to m equilibrium. So there's a plus m equilibrium here, and we have the following dynamics. Asymptotically approaches the equilibrium value. This type of experiment is called inversion-recovery. For obvious reasons. We invert the magnetization and then we watch it recover. And the way we watch it recover is by making it observable and then integrating the signal that we got. Let us think of something different. Let us say, okay, let's not invert it, because inverting it presupposes that originally the system had been in a state of perfect thermal equilibrium, which might take a long time for us to wait to get there. I mean, typically, let's say, in some corundum, right, if you are looking at some impurities, they might be relaxing for hours. Right? What you don't want to do is wait the whole day. What we'll do instead is the following. We will create what's called a saturation train, which is just lots of random pulses in rapid succession that simply just destroys magnetization completely. Then we will wait for a period tau again, then do a pi by 2 pulse, and then do the detection. Whatever managed to recover itself during this time will then be made observable and detected and integrated. So the magnetization will be recovering, but it will be recovering from 0. Let us do the mathematics on what happens in that case. So this is the equation that describes inversion recovery. Let's now derive an equation that would describe saturation recovery, which gives us a different initial condition and therefore a different value for A. So our mz at time 0 in the saturation recovery situation is actually 0. 0, which must be equal to this at time 0, so it's m equilibrium plus A. And therefore A is minus m equilibrium, which gives us a different equation. We will have mz of time, therefore m equilibrium 1 minus just the exponential e minus t over t1. Let's see how this behaves. When time is 0, exponential is equal to 1, and so we begin the dynamics at 0. So the starting point is here. However, when time goes to infinity, exponential disappears and we are still at the equilibrium state. So we will have recovery to the same equilibrium state with the same time constant, but from 0. This is called saturation recovery. And it is slightly more convenient in practice because you don't need to wait between the experiments for the magnetization to fully equilibrate. You just demolish whatever there had been and not particularly worry about it in the next scan. So it's a faster experiment. Okay, now this is the measurement of the longitudinal relaxation rate. In the case of the transverse relaxation rate, there is an additional complication. The complication consists in the fact that the instruments are rarely perfect and samples never actually are. And so what we're going to have is not just spins relaxing, but also spins in different parts of the sample having slightly different frequencies, because we really couldn't get the spectrometer to have a perfectly uniform magnetic field. What is going to happen as a result is, if you plot the Zeeman sphere space, so x, y, z in the rotating frame, if we originally had a bunch of magnetization vectors in the transverse plane, let's say the red vector is pointing exactly at the x, the green vector is also there, and the blue vector is likewise. So essentially this happens with 3 spins after a 90-degree pulse has just been applied. If we wait for a while, however, it may be the case that our red spin is in the bottom part of my body, the green spin is in the top, and the red is somewhere in the middle. Even in the absence of any gradients, they will see slightly different magnetic fields. They will start going out of phase. So what we will have is the same Zeeman plane, but the 3 vectors, even in the rotating frame, will be traveling at slightly different rates. So the red will stay where it was if the rotating frames match to it. The blue one might fall behind, and the green one might go slightly ahead. The problem with this is that if we wait for long enough, they will completely randomize their relative phases. And remember, there are not just 3 spins, there's 10 to the 23 spins. The magnetization basically goes to 0. What we can do, however, is we can apply another pulse. If that's our x-axis, so y and z, why don't we apply a 180-degree pulse in here that is going to just swap them around. So this is tau, and then we apply a pi pulse on x with the result. I'll draw a different projection for that here. So x, y, and z. Well, red spin obviously wouldn't see much because it's being rotated around its axis, so it will stay here. The green spin will be flipped where the blue spin had been. So here, and the blue spin will take its place. Remember, however, that our blue spin was the slow one. It was lagging behind. Our green spin was the fast one. It was going ahead. Well, that still remains the case, right? The green spin is the fast one, so it tries to jump ahead, and the blue spin is lagging. Of course, what's going to happen now is they're going to recollect themselves on the x-axis. So after a while, if we wait for a time tau again, what is going to happen is we return to where we had been, tau. If we look at this in a detection device, oscilloscope or a computer, what will happen is, if that's the transverse, well, the current in the coil as a function of time, then we will originally have some oscillation. So if that's 0, it will be an oscillation that will rapidly decay. Then as we apply the pi pulse, we flip them around, they start recollecting themselves, and the total magnetization reappears. So we will have some reappearance, and then it will disappear again. the phenomenon is somewhat poetically called a spin echo. Right? You clap, give the system a pulse, and after a while you get an echo in your detection circuitry. So this is called an echo. And the beautiful thing about it, even in a non-uniform magnetic field, at the peak of the echo, the magnetization behaves as if the field had been perfectly uniform. Which means that we can actually now measure the transverse relaxation rate. Now, previously, we had two competing processes. One was the magnetization loss due to genuine dissipation, right? Those sorts of things. And the other was the magnetization loss due to the fact that simply just the instrument's a bit crap. And now we've eliminated the second problem. And so actually the way T2 is measured is with the following pulse sequence. You have a pi/2 pulse to make the magnetization transverse. Then you wait for a period tau and give it a pi pulse to refocus. You wait for another period tau and give it a pi pulse to refocus it again, and so on. And what you do is you are running detection continuously through this, and so the result, if that's your signal and that is your time, will be as follows. You will have a signal that initially had a high magnitude, then got itself recollected again, and so on. And your relaxation time is actually the characteristic decay time of this envelope. So it is this that is decay. Right, so here it was perfectly transverse, here it's again recollected perfectly transverse, here it's again recollected perfectly transverse, and so on. You have a picture at the last page of your handout. Now, so this is called Carper cell pulse sequence. Cell sequence. And it is there to measure the T2, and we've already derived the equation for that. It's there. It's just a monotonic exponential decay. Okay, so the summary of what I have to say today is spin relaxation, like rain and tax, is a fact of life. It's unavoidable, and it is predominantly caused by the presence of the noise in the system. I mean, there are exotic kinds of noise, there are prosaic kind of noise, but it is all noise whose spectral power densities and hits the transition frequency, and transitions randomly happen, and so you lose the magnetization. There is microscopic description of relaxation in terms of trajectories of individual little spins. If you average over them, you get an overall apparently exponential decay. This was experimentally found. And then a bunch of guys in the early days of magnetic resonance just said, well, okay, let's just model it with an exponential process. They knew enough chemical kinetics to hook these together. Now, if you remember to add the oscillatory parts, you get these kinds of solutions. For the transverse magnetization, it's just this. For the longitudinal, it rather depends on where you start, hence this constant here. And you can measure these rates depending on where you start, with either inversion recovery or saturation recovery. Inversion recovery has the equations that I've outlined in green, and saturation recovery has the equations that I've outlined in red. It's just simple consequence of solving the corresponding equations. This tends to be a bit more precise, this tends to be a bit faster, but ultimately the choice is yours. The complication in the case of the transverse relaxation is we have to deal with realistic equipment in which uniform magnetic field is basically unachievable. So no point even trying, because, for example, the susceptibility gradient across the sample, there is nothing you can do about it physically. And so there will be two competing processes, one genuine relaxation, where that goes exponentially to zero, and the other is dephasing due to the magnetic field being bad. We can get rid of the dephasing by this spin echo technique, As the spins start going out of phase, we just flip them around and then recollect themselves, and that's called a spin echo, because it looks like an echo on the oscilloscope. And then we can just have pulse, then echo 1, echo 2, echo 3, and so on. The echoes will happen in the middle of these intervals, and we can measure the peaks of the echoes, and that is the dynamics of the genuine transverse magnetization that's isolated from the instrumental effects. Called Cowper cell sequence, and that's how you measure T2s. And we will put both T1s and T2s to good use in the protein NMR spectroscopy when I come to that, and Marcel will put them to good use in magnetic resonance imaging, because these are the two principal sources of contrast in MRI. Any questions?